A simple start. Have you ever wondered how your phone knows which faces belong to your friends? Or how your favorite streaming service suggests a movie you end up loving? The answer is a powerful technology called machine learning. In simple terms, machine learning is the science of getting computers to learn and act without being explicitly programmed. We do not write step-by-step rules for every single task. Instead, we give the computer data and let it figure out the patterns on its own. It is a way for computers to learn from experience, much like how we humans learn new things every day. This ability to learn from data is transforming our world in countless ways. The impact of machine learning is all around you, often in ways you might not even notice. It is working quietly in the background, making our lives easier, safer, and more interesting. Let's look at a few examples from our daily lives. Imagine you own an ice cream shop. You might notice that on hotter days, you sell more ice cream. Machine learning can take this simple observation and turn it into a powerful prediction tool. By looking at weather forecasts, a model can help you predict exactly how much ice cream you will sell tomorrow. This helps you prepare the right amount, so you never run out on a sunny day or have too much melting when it rains. Now, let's consider a more serious application in the field of medicine. Doctors have a lot of information about their patients, such as their age, weight, blood pressure, family medical history. A machine learning model can analyze this data from thousands of patients to find hidden patterns. It can help a doctor identify if a new patient is at a high risk for a certain disease, like heart disease. This early warning allows the doctor to recommend preventative actions, like changes in diet or exercise, potentially saving lives. The computer is not replacing the doctor. It is giving the doctor a powerful new tool to make better, more informed decisions for their patients. Finally, let's think about how scientists study the natural world. Imagine a researcher in Antarctica studying penguins. They need to identify the species of each penguin they find. They can measure things like the length of the penguin's bill, the depth of its bill, the length of its flippers. Instead of relying on a field guide every single time, they can use a machine learning model. After being trained with data from hundreds of known penguins, the model can look at the measurements of a new penguin and quickly tell the scientist if it is an Adelie penguin, a chinstrap penguin, or a gentoo penguin. This makes research faster and more accurate, helping us better understand our planet's amazing wildlife. At the core of machine learning are two fundamental processes: training, inferencing. Training is the learning phase. This is where we show the computer a lot of examples. Think of it like teaching a child to recognize a cat. You show them many pictures of cats, pointing each one out and saying, "cat." The child's brain starts to build a mental model of what a cat looks like: fur, pointy ears, whiskers, tail. In the same way, we feed a machine learning model lots of data so it can learn the underlying patterns. For our ice cream shop, we would give the model historical data showing the temperature and the number of ice creams sold each day. Once the model has been trained, it is ready for the next step. This is called inferencing, or making predictions. This is the doing phase. After seeing many pictures of cats, a child can see a new animal and correctly say, "That's a cat." The child is using their learned knowledge to make a prediction about something new. Similarly, our trained machine learning model can now take new, unseen data and make a useful prediction. For our ice cream example, we can give the model tomorrow's weather forecast, a temperature it has never seen before, and it will infer or predict the number of ice creams we are likely to sell. This is the ultimate goal: use past data to make accurate predictions about the future. To understand this process, we need to know about two key terms: features labels. Features are the input variables we give to the model. They are the pieces of information we use to make a prediction. In our examples, the features, often called X, would be temperature for the ice cream shop, patient's medical data for the doctor, penguin's bill and flipper measurements for the scientist. These are the clues the model uses to solve the puzzle. The more relevant and high-quality features we provide, the better our model will be at learning the patterns hidden within the data. The label is the output variable, the answer we want to predict. We often call the label Y. In our ice cream example, the label is the number of ice creams sold. For the medical example, it is whether the patient is at high risk or not. For the penguins, it is the species of the penguin. During training, we provide both the features, X, and the corresponding labels, Y, so the model can learn the relationship between them. Our goal is to create a model, a mathematical function, F, that maps inputs to outputs. This relationship is represented by the simple formula, y = fx. When we give the model new data without a label, it predicts the label. We call this prediction y-hat, y with a little hat. Machine learning is a big field, but most tasks fall into one of two main categories: supervised learning and unsupervised learning. Supervised learning is the most common type. The name supervised comes from the idea that we are acting as a supervisor or a teacher for the model. We give the model a data set that contains both the features, X, and the correct labels, Y. The model's job is to learn the mapping from the inputs to the outputs. It looks at the labeled examples one by one and adjusts its internal parameters to make its predictions as close to the true labels as possible. It is like giving a student an answer key with a practice test to help them learn. Within supervised learning, there are two major types of problems: regression and classification. A regression problem is when the label Y we want to predict is a continuous number. Our ice cream sales example is a perfect case of regression. We are trying to predict a specific numerical value, the number of ice creams we will sell, which could be 50, 102, or 350. Another example would be predicting the price of a house based on features like its size, number of bedrooms, and location. In regression, the goal is to predict a quantity along a continuous spectrum. Classification, on the other hand, is when the label Y we want to predict belongs to a limited number of categories or classes. If there are only two possible outcomes, it is called binary classification. Our medical risk example fits here. The model predicts one of two classes: high risk or not high risk. Another example is an email spam detector: spam or not spam. If there are more than two categories, it is called multi-class classification. Our penguin species problem is a great example: Adelie, chinstrap, Gentoo. The second main flavor of machine learning is unsupervised learning. In this case, we give the model a data set that only contains features, X, but no labels, Y. There is no answer key. The model's job is to explore the data and find interesting structures or patterns on its own, without any guidance. The most common type of unsupervised learning is called clustering. A clustering algorithm tries to group similar data points together into clusters. For example, a company could use clustering on its customer data. The algorithm might find natural groupings of customers based on their purchasing habits, creating clusters like frequent shoppers, weekend bargain hunters, and occasional big spenders. This helps the company understand its customer base better. As you go deeper into the world of machine learning, you will often hear the terms deep learning and neural networks. Deep learning is a specific subfield of machine learning that has become incredibly powerful in recent years. It is particularly good at finding very complex patterns in large amounts of data, like images, sound, text. The technology behind deep learning is inspired by the structure and function of the human brain. Our brains are made of billions of interconnected cells called neurons, which work together to process information and help us learn. Deep learning models try to mimic this structure. These models are called artificial neural networks, or just neural networks for short. A neural network is made up of layers of interconnected nodes, or neurons. The simplest network has an input layer where we feed in our features, X, an output layer which produces our prediction, Y, and one or more hidden layers in between. Each neuron in a layer receives inputs from neurons in the previous layer, performs a small calculation, and then passes its result to the neurons in the next layer. The deep in deep learning simply means a neural network that has many hidden layers. These hidden layers are what give deep learning its power. Each layer learns to recognize different features in the data at different levels of abstraction. For example, if we are training a neural network to recognize faces and images, the first hidden layer might learn to detect simple edges and colors. The next layer might combine those edges to recognize shapes like eyes, noses, and mouths. A subsequent layer might then combine those shapes to recognize a full face. By stacking these layers, the network can learn incredibly complex and hierarchical patterns that would be very difficult to find with other methods. Deep learning has been the driving force behind many of the most impressive AI breakthroughs we see today. It is the technology that powers self-driving cars, enabling them to see and understand the world around them. It is used in voice assistants like Siri and Alexa, allowing them to understand your spoken commands. So, how does a machine learning model actually learn? It is not magic. It is a systematic process we can break down into several simple steps. This process is often called the training loop because we repeat it over and over to make the model better. The very first step is to prepare our data. A crucial part of this is splitting our data set into at least 2, and often 3, separate parts: a training set, a validation set, and a testing set. The training set is the largest part, and it is what we use to actually teach the model. The model looks at the features and labels in the set to learn the underlying patterns. The next step is to train the model. We take our training set and feed it to a machine learning algorithm. The algorithm looks at the examples one by one, or in small batches, and tries to make predictions. Initially, its predictions will be completely random and very wrong. But after each prediction, it compares its guess Y to the true answer Y from our training data. It then calculates how wrong it was. This is called the error or loss. The algorithm then makes a small adjustment to its internal settings to try and reduce this error the next time. This process of predict, check, and adjust, predict, check, and adjust is repeated thousands or even millions of times. After the model has been trained for a while, we need to check how well it is learning. This is where the validation set comes in. This is a part of the data that the model has never seen during training. We use the validation set to get an unbiased look at the model's performance. It helps us answer questions like, is the model actually learning general patterns, or is it just memorizing the training data? We use the results from this validation step to tune our model. For instance, we might decide to let it train for longer, or we might adjust certain settings called hyperparameters to improve its performance. This leads to the iterative nature of the process. We train, we validate, we evaluate our results, and then we repeat. We might go back and try a different algorithm, adjust the hyperparameters, or even add new features to our data. This cycle continues until we are satisfied that the model performs well on the validation data. Finally, once we have a model that we are happy with, we use the testing set. This is a final, completely unseen portion of data that gives us the ultimate report card on our model's performance in the real world. This step ensures our evaluation is honest and tells us how the model is likely to perform on brand new data. After we train a model, we need a way to measure how good it is. Just saying it seems good is not enough. We need specific numbers, metrics, to evaluate performance objectively. The choice of metric depends on the problem type. For regression problems, where we predict a number, common metrics are MAE, MSE, RMSE, and R-squared. MAE, mean absolute error. It computes the absolute difference between prediction, Y, and actual Y. Then it averages those differences across examples. Example, May of 10 means we're off by 10 ice creams on average. MSE, mean squared error. Instead of absolute differences, it squares the errors before averaging. Squaring penalizes large errors much more than small ones. 10, 100, 2, 4. If we predict 50 but actual is 250, MSE blows up, flagging a big mistake. MSE is in squared units, so it's hard to interpret directly. RMSE, root means squared error. RMSE is the square root of MSE. That returns the error to the original units, ice creams. RMSE of 15 means typical deviation is about 15 ice creams. R squared, coefficient of determination. It measures how much of Y's variation is explained by X. Scores range from 0 to 1. 0 means no better than predicting the mean. 1 means perfect explanation. 0.85 means 85% of variation explained by temperature. A very good fit. Today, we have taken a quick but important journey through the fundamentals of machine learning. We started by demystifying the concept, defining it simply as a way for computers to learn from data. We saw how it touches our lives through everyday examples like predicting ice cream sales, assessing medical risk, identifying penguin species. We uncovered the core ideas that make machine learning work. We learned that the process involves training a model with data and then using it for inferencing, making predictions on new, unseen data. We explored the key vocabulary you will need. Features, X, are our inputs. Labels, Y, are the outputs we want to predict. The relationship is Y, Jax F, X, and the model's prediction is Y hat Y. Two main types of learning. Supervised learning, labeled data. Unsupervised learning, model finds patterns. We briefly touched on deep learning and neural networks inspired by the brain. Practical steps. Split data into training sets, validation sets, testing sets. Then iterate. Training, evaluating, refining. Evaluating models requires metrics. For regression, we covered MAE, MSE, RMSE, R squared score. These tools tell you not just if a model works, but how well. These concepts form the bedrock of most ML and AI applications. This essay is the first step on an exciting path. You now have a solid conceptual foundation. You can understand ML language and explain its basics to others. Next, start applying these ideas. Use online courses and hands-on projects to build skills. Keep learning, stay curious, and start building. The world is full of data. You now have the key to unlock its insights. Your journey has just begun.